Welcome to the last session on rational functions. We are ready to take on the partial fractions. Please listen to this lecture video very well and know when partial fractions become handy. So let's take the introduction to partial fractions. My slide says that partial fractions become important when I have a complex rational function. So let me change this to some blue. When I have a complex rational function, we'll get to know when it is complex. If it's complex, I can break it down to two or more simple partial fractions. So from complex to simple terms. For now, don't ask when is it complex. We'll get to know it very soon. So like the example I have here, it has been able to express what is on the right hand side into two partial fractions. And indeed, if you should add them, this is a rational function. Don't forget, it's a polynomial on a polynomial. So this guy here, we are looking at addition of rational functions. You know how to add. You find the LCM, you expand, and then you simplify. So we expand here. We are doing multiplication expansion. If you simplify, you end up getting your right hand side. So indeed, that simple two terms here, these two simple terms here, was a decomposition of the rational function. And that's how beautiful partial fractions are. And the next question we will ask ourselves is, how do I get to use this partial fraction? Or how do I know that I was supposed to get 2 and then 3 as the numerator? That is what we want to talk about now. If you want to use partial fraction decomposition, the focus is on the denominator. Is that how to spell focus? Or our concentration is on, so it's CU. Yes, our concentration is on the denominator. So if I have P of X over Q of X, this is a rational function. My concentration is on the Q of X. Now this Q of X can be linear. It can also be a quadratic form. Please, since Q of X is a polynomial, you know why, or you know when it becomes a linear. Linear means degree of 1. Quadratic means degree of 2. You realize that we are building up on polynomials. So this thing shouldn't get confusing. In as much as we have linear and quadratic, we can have these terms also repeating. And we'll look at it very soon. So our focus is on the Q of X. Alright. Now there are ways we can express this denominator, the partial form of our denominator. Case 1 is when it is linear but distinct denominators. It means I'll take it one after the other. I'll write A over the denominator 1, A over the second Q2, A over the third Q to the last Q. I don't know if this is well understood. So that's a linear factor. If the degree is 1, it has several of them. You take A, B, 2 to the last term, as you can see in table 11. If it's quadratic, we write the numerator as A plus BX over the first QX. So I think in place of D1, I could rather make it Q1, Q2 to the third term. And look at how the numerator has been expressed. The numerator is of the importance here when it comes to writing the partial. So the first, the second, the third, through to the last one. Okay. In a case where they are repeated and it is linear, so I want to use the Q's. In case where they are repeated, so you have your first one is equal to the second denominator is equal to the third denominator. They are the same, equal to the end. The first A takes the first denominator. The second B takes the repeated square. It means the third will take cube through to the same thing n. If it's repeated twice, it means I end here. If the denominator is repeated 3 times, I move to the next stage. That is how it is. If I'm looking at quadratic and it's repeated, the same thing, I maintain the numerator, but here becomes square, the third through to the last form. I'm not so sure if this went well, but let's look at the smart guesses and then you get to appreciate it. Okay, so the examples here. We have a rational function. We want to know the type of the denominator. It is linear because the degree is 1. Whatever is here, the degree is 1. It is linear and then it is repeating. Repeat. So it means that my partial form will be a over the first term plus b over the second term squared. It is repeating twice. If here has been 3, in place of 2 has been 3, and then I'll add c over the same denominator to the power 3. Okay, so that is it for the repetition, but we had it as square, so let me maintain the square. In the second example, the concentration is on the denominator. It is 2 linear factors, 2 different, so they are not repetitions. So I simply have a over the first factor plus b over the second factor, and I'm done. If there was additional factor, say x plus 1, then I'll have it as c over x plus 1. Okay, but we don't have it there, so let me take it off. Okay, then the third example, what do we have here? The degree is 2, so it means it is quadratic. Is it repeating? No. So my partial form become ax plus b over that simple term. Okay, the next example, the degree is 2, so it means it is quadratic. And there's a square here, it means it's repeating. So how do I write the partial form? The first is ax plus b, s squared minus 2. How many times is it repeating? 2 times. So plus c plus dx over s squared minus 2 all square. This is how the repetitions are done. Now the last example, I have a linear factor. Degree here is 1. Degree here is also 1. So I have linear here, linear for the first term. The second term is also linear but repeating. So I'm adding these terms. So I have a over x minus 2 plus b over x minus 3 plus c over x minus 3 squared, because this part is linear and repeating. So that's how the partial fractions are being formulated. I hope that wasn't difficult to do. You can take more examples and see how you can express the partial form of them. Okay, now the question is, you realize that you've introduced some a, b, c's in your original function. The next question is, how do I solve for these fractions? We are done with the smart guesses. So examples, how do I solve for these unknowns? It is important we solve for them. Again, because we are looking at rational functions, there are 2 forms of our rational functions. I'll take the first one, the proper, and then look at the improper one. So we go back to the image we saw at first. How do we arrive at 2 and then 3? That is the question we are asking. How do I know it is proper? I will not answer that question. We've done that in the first lecture video. So I can factorize the denominator into this. And because when I'm done, so I'm done with the factorization, the next thing is write the partial form Because it's proper, I can easily factorize it. So step 1, step 2, I write the partial form of it. I look at the denominator here. There are 2 linear terms. It is not repeating, they are just 2 linear terms. So A takes that, B takes that. So A over x minus 2 plus B over x plus 1. If you're able to write this one first, then you know you're on the right track. If you're not able to express the right partial form, your answers are wrong. And when you do the expansion, you will not get the answer. So let's continue. Step 3, I have to find the LCM. And you realize I'm going to get some A of x plus 1. This is easier to do, x minus 2. Let me just expand this thing for here, or it's not necessary. Okay, sorry for the interruption. Okay, when I find the LCM now, I can expand and simplify. Step 4, I expand. When I expand this, I'll get, this will lead me to ax plus a, and then this leads me to bx minus 2b. These are simple expansions. Then I can compare the coefficients. I left the denominator out because this is equal, they are the same. So I want to compare the upper parts, that's the numerator. That is where I can find my unknowns a and b. And so it means that my numerator here, then I group like terms. If I group like terms, realize that this will take this guy, and then this a will take this 2b. That is how I've grouped the like terms. Then comparatively, x will be compared to the x, and then the constant will be compared to the constant 4. It means I have 2 simultaneous equations to solve. We know how to solve simultaneous equation, whether by elimination method or substitution method. That is up to you to do. If you do it well, you end up getting a equal to 2 and b equal to 3 as the answer. So it means that my rational function here has been expressed to some simple simple form by the help of the partial fractions. This shouldn't be difficult to do. It's about you first being able to write the partial fraction first. So I'll use a color red to highlight what I mean. If you're able to write this one, that is all. You find your LCM, you simplify, you compare. That is the most important part of the work. So we've proved how to get the 2 and then the 3 from the preamble, and that is as simple as that. Now the next example on the slide, so I have to scroll so many times because of my pauses. It says express 2x. I was told the red pen in writing is not so clear, so let me just undo and use the black as usual. Express 2x plus 5 over 3x squared minus 12x in a partial fraction form. There's a complex rational function because I can't easily do the long division, or you can. It's simple to do if you want to. It's even cubier. So I have to test, is it proper? Degree of the numerator is 1, degree of the denominator is 3. 1 is less than 3, since hence it is proper, so I can factorize the denominator. How to do that? You should be able to do it by now. So let me check what I had. I had 2x plus 5 all over 3x, x plus 2, x minus 2. The most important thing is to be able to write a partial form. Now look at it. Degree here is 1, degree here is also 1, degree here is 1. So I have 3 linear factors. It is always cool if you have linear factors because they become easy to solve. It means I have a on 3x plus b on the second term. There is no repetition. C on the last term over whatever I had here. What do you have? So this is a partial form, and that is what I need. From here you can find the LCM, you expand, and then you compare coefficients, just as I've done in the first example. What will be the LCM? You're just going to take all of it. So the upper part here, I'm sure we have A taking x plus 2 and then x minus c. B will take 3x and then x minus c, and then c will take the last 2, x plus 2. You expand and then you compare it to just 2x plus 5. Okay, that is it for this example. You can continue in your jotter. Now the interesting part is to move to, so when you solve this, a is -5. Let me go back and write the answers for you. When you solve this, a will be -5, b is 1, c is 3. You can confirm these answers. Okay, now the next one is the improper fractions. For proper fractions 15, we can factorize and we move on with the partial form. Improper means the degree of the numerator is greater than or equal to the degree of the denominator. Let me use a different ink here. Okay, and we said that if I use a long division, I'll end up getting a form as this. We know what Q is. Q is a quotient, R is a remainder, the small q is a divisor, which is always provided. Indeed, this is already in the partial form or the partial fraction form. Now the improper becomes handy with the partial form if it's complex to find the long division. Some of the questions it will be easier to use long division, others might not be easier to use long division, and this is when partial fractions become very important, especially with the improper one. So the question is, how do I find q of x if it's complex? So let's say if I can't do long division to get it, if I can't do long division to obtain it, this is how you obtain your q of x. You find the degree of your numerator, let's assume it is n. You find the degree of the denominator, let's assume it is d. Then q of x becomes a polynomial of degree n minus d. That is how your q of x would be. And then your rx over qx becomes just a partial fraction respect to a denominator, as simple as that. So it means that this is of the interest. This is what we must find if the long division approach might not be so simple to do. It is a polynomial of degree. Now check the slide 17. Before you go through polynomials, if it's 0, it means it is constant. That is, if your n minus d is giving you 0, it's a constant polynomial. I add a to it. If it's giving me 1, it is linear, and that is a linear form. If it is 2, it means I add a quadratic form to this part, to the partial fraction part, and so on and so forth. So that is how the q of x it is obtained. I'll take it through 2 examples for you to appreciate it. So let's take example 1. It says express this rational function as partial fraction. I'll go through the 2 approach. So example 1, case 1, I'm going to use the first let me find the degree. Degree of the numerator is 2, degree of the denominator is 1. 2 is greater than 1, hence I have improper. It means I have to use a long division approach if it's easier to do, or I can do the partial fraction form if it's difficult to do. I have just a binomial polynomial at the denominator, so I can easily do long division. If you go to the long division approach, you have a remainder of 1, trust me, and it means that you are going to get quotient. So it means, let me do it with this correct here. This is how my Q of x, my R of x, and then my divisor would be like. This means that the 3 minus x is my quotient, which is from up here. I'm not going to do the long division, we've already done so many examples of it. My remainder is what I had here, the 1. My divisor is this guy here. So long division can help you in this case as simple, but the question says we should use a partial fraction form, and let's see if we're going to get the same answer. Okay, so case 2, what do I need to add? I wish I cleaned certain parts. Let me write this guy here for you. We had 3x minus 1 plus 1 over x plus 1, and we said this is the same as, okay, so I can clean this one now so I can have some space for some analysis. So this is your Q of x plus your R of x over the divisor. That is it. If I don't want to use the long division approach, but it says use a partial form, that is the case 2 I'm trying to do now. I should have left more space. The question was 3x squared plus 2x. I think I want to use a different ink to make it different for you. 3x squared plus 2x all over x plus 1. Degree of the numerator is 2, degree of the denominator is 1. This is the n, this is the d, and so I need to add degree of n minus d, which means I have 2 minus 1, degree of 1. I have to add a polynomial of degree 1. If I go back to slide 17, degree of polynomial 1 is this one here, so this is what I have. I add it to the partial form. The partial form, if I look at the denominator here, it is a linear, it is just one linear term, so I have c over that. Do you see any difference here? This is the same as writing Q of x plus R of x over the divisor. Divisor is known, remainder is not known, quotient is not known. So either you use a long division approach to get them, or the partial fraction form. You realize that in the first example we had 3x minus 1. This means your a is 3, b is negative 1, and c is 1. Let's see how we can get that. Again, I find the LCM here. You should be able to find the LCM by now, and then this is what I'm going to get. What do I do next? I expand and compare coefficient. If I expand this, I'm going to get the whole of this part, and then plus the c here. Take your time and do this expansion. Now what I did was to group like terms. So those with x squares, those with x, and then those as constants here. Now when I compare the coefficients, we are still in partial fractions. When I compare the coefficients, you realize that the x square here can be compared to this guy, the x part will be compared to these ones, and then the constant will be equated to 0. So automatically I have a to be 3 from the first equation 1, from equation 2, equation 3. From equation 2, realize that then b becomes the 2 minus a, which becomes negative 1 because a is 3. From equation 3, change of subject, C becomes negative B, which is just 1. So this is how simple it is. Don't forget we wrote it as the added polynomial and then the partial form. So A is 3, B is negative 1, C is 1. How different is this answer from the long division approach? It is the same answer. Probably you didn't catch the revelation. Take your time and go over this lecture video. So you won't either use the long division when it's possible. If not, you can use a partial fraction to get the same answer. Now let's look at the second example. So here I use a partial form. Look at the second example here. Realize that in this case the degree of the numerator is 2, degree of the denominator is 2. This makes it improper. So I can't factorize. I have to use the long division. But long division here will be quite difficult to do. As I haven't, you're looking at s squared plus s plus 1 divided by s squared plus 2s minus 1. You can easily do this. You get the same answer, trust me, which I'll do afterwards. But assuming I don't want to go to this long division approach, I want to use partial form to solve this rational function. I know because it's improper, I'll end up getting a relation like this, where Q is my quotient, R is my remainder. If I should use a long division, this is my divisor, and this is the quotient. Okay, but we solved, or we showed how to get the Q of x. Q of x is what you add. So this guy here, I can easily find it because this is a degree of 2. It is quadratic. Quadratic polynomial partial form will have ax plus b over whatever term you had there. But first, let's find what the qx would be. The qx becomes adding a polynomial of degree. So n is 2, n equal to 2, d is also equal to 2. So degree of n minus d will give me degree of 0. I don't know why I'm writing this, but I hope it is clear up there. Let me write it somewhere else. Degree here is 2, that is n. Degree here is 2, that is the d. So it means I need to add a degree of the form n minus d. That will be 2 minus 2, that is 0. A polynomial of degree 0 is a constant polynomial. It means my q becomes a, just a simple a. And then whatever I have there becomes the quadratic factor, bx plus c over the divisor. I hope this is clear now. From here, what do? I find the LCM. I go the same process. I expand and then I simplify. All those with s square, all those with s, and then the constant values comes in. I don't know why I use x here, but the question is in terms of s. Forgive me for that. And then I compare coefficients, s squared plus 2s plus 1. This s squared will be compared to this guy. Those with s will be compared here, and then the constant will be compared to this guy. So it means I have 3 simultaneous equations to solve, and these are very simple. From equation 1, a is just 1. From equation 2, I can find b. From equation 3, I can find c. And what would this be? If a is 1, it means b becomes 2 minus 1, that would be 1. And then c becomes 1 minus 1, which is 0. So it means that my partial fraction, or this rational function I had here, which was q of x plus rx over the divisor, I had k of x to be a constant polynomial plus the partial fraction, some c, what do I have here, cx plus bx plus c all over the divisor. I've already found for b, and 1 plus 1x, so that is x, plus 0 over the divisor is, I don't know why I'm still using x. I think I'm used to x, so it is s over s squared plus s plus 1. B we had as 1, so s. C we had as 0. And that is it for our solution. A is 1, B is 1, C is 0. And that's it. You can go ahead and use the long division approach and see if you can easily get the same answer. And trust me, you are going to get the same answer. Okay. So now this gives us to problem of the day. Problem of the day says we should find the partial form, but it is given us in the form of integral calculus. This means that partial functions are used in calculus, integrals, and differentiation. We are asked to find the missing terms if we want to compute this integral. If I want to compute this integral, we are finding just the missing terms, not the entire integral. So I'll give you a clue. If I look at the denominator here, the degree of the numerator is 1, degree of the denominator is 2. If I expand, I'll get x squared, and there's the proper, it's already factorized. So I check here, I have 2 linear terms, and so A takes the first term, B takes the second term. And what do? I find the LCM, I expand. When I expand the numerator, this is what I'll get, and the B part, this is what I'll have. This will give me the B part, this will give me the A part. Check it out. Then I compare coefficients just by the numerator. If I compare coefficient, because there is no constant term, it goes to 0. So this will be compared to that, but this will be compared to certain 0. It means I'm solving 2 simultaneous equations, and I'm not so sure what the answers would be, but whatever A you get, that is what you place here. And this is how simple the integration will be solved. And so I hope the partial fractions has been helpful. In our next section, that is unit 7, we'll take the arithmetic sequence. Please, I need to confirm this using the long division approach. So I've shown you how to use the partial functions. If you're not so much convinced and you still want to go to long division, you are good to go. Okay, thank you. See you in the next lecture video.